Everybody, welcome to the webcast. My name is John Ziola. We're going to be talking about the supply chain today. It's going to be fun. So this talk is part 3 in a 4-part series on the cloud flight simulator. So we've got one more. If you've missed them, we've got recordings of the others as well. In this part 3, we're going to be talking about safeguarding the software supply chain. So a little bit about myself. My name is John Ziola. I'm a SANS Sec 540 instructor. So that's the Cloud Security and DevSecOps Automation class. I'm also the co-founder and CTO at a company called CISO, where we do cloud native security and compliance work. So things like SOC 2, ISO, and cloud native environments, kind of the intersection of those two. That being said, I love low friction cloud native security and compliance, but I also love walking desks. So this is one of the few times during the day where I'm not walking on my treadmill, which is right over here to my side. If you want to talk to anybody about walking desks, I'm your man. I am also a CNCF ambassador. So there's about 20 or 30 of those ambassadors in the US. The CNCF, if you're not familiar, is the organization which holds Kubernetes and the whole Kubernetes cloud native ecosystem. So I'm one of their US-based ambassadors living in Pittsburgh, Pennsylvania, and also the recipient of the 2021 Startup Innovator of the Year Award. Also, yes, that picture is AI generated. But if you see me online, I'm probably using that picture or something similar to it. All right, so a pretty short agenda for today. We've got just 4 main parts to the conversation. We're going to kick things off just talking about modern software development. That'll be very brief. We will do an introduction to supply chain security. There's a few definitions here. This is a bit of a subclass or a subspecialty of cybersecurity, so there might be a few terms that'll be new to you. We'll cover those, and I'll try to reinforce those as we go. I will have a demo. We'll do some salsa provenance. We'll look at software bill of materials, hands-on, a couple things like that. And then we're going to wrap things up with what it looks like after you've rolled out some initial supply chain security. So it's great to start implementing some of these techniques at your company, but what happens on day 2, day 3, 1 year out, 2 years out? How do you manage all these different artifacts? What do you do with them? How do you actually use them to improve your audits and to improve your security? So we'll talk about those kind of like day 2 challenges and techniques. All right. So very brief introduction to software supply chain security. So what is this? What is the topic that we're covering today? Well, software supply chain security is methods to enrich software development practices, right? The goal here is to add on top of traditional software development practices to provide better assurance, to be able to prove to other parties that the development of the software and the creation of the artifacts, those packages, the containers, that was done securely and that they have maintained integrity, right? We'll talk about all kinds of different language that we can use to describe those properties, but that's really what we're trying to do here. We're trying to be able to prove to other parties that the software we have or the software that we're using is safe, or at least we know where it came from. It hasn't been tampered with. And so this has become a really popular topic over the past few years. If anybody's heard of the SolarWinds compromise, that kicked off a lot of response activity, including from the US White House. So in May of 2021, there was this executive order on improving the nation's cybersecurity, EO 14028. And so while that happened in 2021 and was predominantly in response to the SolarWinds compromise, which affected a lot of large companies and governments alike, this is not a new problem. A lot of people will think back to Ken Thompson's 1984 acceptance speech called Reflections on Trusting Trust, where he described how he backdoored a compiler in the 70s, and it was kind of like a thought experiment on how do you trust the compiler that compiles your code to not put backdoors in it? How do you trust the debugger? So if you're going to debug the compiler, that it will actually tell you that the backdoor is in the compiler, right? We've got this turtles all the way down. Like, how do you trust that? How do you trust that? How do you trust that? So this has been a problem since the 70s, but really is a huge and on a huge uptick recently. And Sonatype has my favorite metric for this. So in their 2021 State of the Software Supply Chain, they showed a 750% increase. So that's a 750% increase on the prior year on 2020. If you see the graph, it's great. It's got a massive spike in it. And this is a continued problem. I think that we're only seeing these attacks, these supply chain attacks, become more and more frequent in the ecosystem. And one of the things that I do in the CNCF is I'm a member of the technical advisory group for security, and we maintain a list of compromises. So I've got a link here. If you want to go to that, you can see supply chain security specific compromises that we curate. It's just a bunch of markdown files where we describe based on the year what things have happened, going all the way back to the 80s, but also more recently in the 2000s and the 2010s. So there's a lot of popular techniques in this supply chain ecosystem. You'll see things like provenance, signatures, cryptographic signatures, SBOMs or software bill of materials be thrown around. Those are the sorts of things that we're going to talk about today. There's also properties, right? These properties of an environment that are really a focus of software supply chain, like immutability, right? Not being able to change something. And ephemeral components, creating something from scratch from an immutable base, using it, running something in it, and then throwing it away, right? With the advent of cloud service providers and cloud resources and all of the automation that we have today, we're able to create a server, use it for something, and throw it away. Or maybe we just create a process on a server, like a container, and we can scope it. We can reduce the file system permissions that it has, the user namespace, network access, process namespaces, all of these different things, the amount of RAM and CPU it can have. We can constrain it and do our work and then throw it away. That's the kind of base idea here. A lot of immutability and ephemerality. But I promised we would briefly talk about modern software development. So if you've written code in the last few years, you've probably followed a pattern similar to this, right? So starting with number one here, we've got version control. In most companies, and by most companies, I mean 90-something%, it's going to be Git based. So that's what we got, GitHub and Bitbucket and GitLab and all of these really popular version control systems, mostly going to be Git based. And Git has a concept of branching, and typically you'll have what's called a main branch. You can see that here. That's where all of the code that is ready or done should live. Now, if you want to add to that code, you don't make changes directly to it. In fact, you make a different version of history. You branch out, you make a feature branch, and you make whatever changes you'd like, and you're not affecting that kind of approved final part of the code. When it's ready, when the feature is done, when you've written tests, you've done your security scans, you can submit a merge request or a pull request. That just means I've got some code changes. I would like them to be included in the kind of final version of the software. Typically, that's where you get peer review and then approval, a merge, and then CI/CD, right? In CI/CD, you'll have automation run to deploy into different environments. Maybe it's going to package up and put it on Docker Hub. Maybe it's going to go to your JFrog Artifactory, your Sonatype Nexus, maybe AWS ECR or Azure ACR, wherever it lives is a part of the CI/CD process. And when developers are writing code, their interface is probably going to look a little bit something like this. This is a screenshot of one of many of the components of the SANS Cloud Flight simulator. This is our developer environment. You can see we've got all kinds of different repositories on the left, different types of code. We've got Java code. We've got pipeline definitions. We've got infrastructure as code, a bunch of Terraform files, all kinds of different stuff. We've got a terminal at the bottom. We've got this big area up here where we can store files. I'm going to do a demo that kind of shows this a little bit, but developers are going to open up some files from these Git repositories and make changes. Add code, add functions, add business logic. Open that merge request. And once they get peer review, their CI/CD pipeline should run. So here's an example of a GitLab CI/CD pipeline that goes through a bunch of different steps, right? We want to test it. We want to build the artifact, probably want to scan it for security issues, package it up and store it somewhere. Maybe we're going to just deploy it and store it in an artifact repository, or maybe we're going to go all the way to pushing it into a cluster, right? So that's how software development works today. And as a part of that process, there are a lot of potential for attacks. So this is a picture that comes from the SLSA project, which we'll talk about a little bit later, but the goal of SLSA is to improve the software supply chain. And you can see A through H, all kinds of different problems, starting from when you have source code, when you just are looking in your IDE at code. If an attacker compromises a developer's credentials, could they use those? If they compromise the server, in the couple slides back, we showed GitHub. If they compromise the GitHub server, can change some configurations, push commits to it there. That's another sort of issue. Then it'll go to build, right? It'll go to that GitLab CI/CD pipeline. Bad things can happen there too. It could pull from an untrusted source. You could have issues whenever you try to build a package, and then when you want to store that package somewhere, or when you want to consume that package to actually run on your servers, right? The goal here is just to illustrate there are tons of different problems. The things that we're going to talk about next typically do not solve all of these problems all at once. There's a lot of matching of one technique to one or a handful of these issues, but none of them solve all of these problems. You can't just implement software bill of materials and say A through H, you're good, right? Software bill of materials can solve some of these problems. We'll talk about what it helps with, where its pain points are today. But just know that this is not a single point solution ecosystem. There's lots of different problems. Currently, we need lots of different types of solutions. And there are some attempts to connect together those different solutions to make them easier to implement, but we've still got lots of them today. I am coming off a little bit of strep throat, so I'm going to take a sip of my tea. Excuse me. All right. So let's talk terminology. I promise this is the only terminology slide, and these terms were cherry-picked because it's the ones I'm going to keep using throughout this presentation, right? Starting with artifact, right? So we've got our source code software, and then we want to, maybe in that source, we've got a bunch of individual files. One of those files could be an artifact. More commonly, when we're talking about artifact, we mean a bundle of files, maybe just zipped up, right? Maybe a Git repository just zipped up into a file, or turned into a container image, or turned into a software package, right? So you take your source, you do some sort of processing to it, and typically out comes an artifact. Then in supply chain, we've got these attestations. Attestations are metadata that is authenticated, right? This is additional context. In attestations, there's lots of different types of attestations. All we're saying is an attestation is some person or thing attesting to metadata about an artifact, right? I am saying that this container image came from my CI/CD pipeline. Provenance is a specific type of attestation, right? Provenance is an attestation that is focused on what happened to make this. What environment was used? What did your CI/CD pipelines look like at the time of creating an artifact? What arguments were passed into the compiler? What steps were taken to create this? What did you do to initialize the environment? What commands did you use? And what version of your Git repository was it? What version of the scripts was it? Lots of immutability here, lots of pointing to hashes, either git commit hashes or SHA-256 hashes, in order to describe what happened. This is historical, right? We are attesting to what happened in a pipeline, how an artifact was created or produced. And so that pipeline, that is the build process. There's a system involved. There's a server somewhere. It might be serverless, but there's still a server, right? We take the inputs, we take all of these configurations and scripts and a runtime environment and source code, and we build something. We are making an artifact. And during that build process, you've got probably lots of different dependencies. So you've got to pull those. Maybe they get passed in. Maybe you use hermetic builds, which is not very common, but a build process that has no network connectivity. It's possible. So then all those dependencies need to be passed in, but you still need to pass in dependencies. Or what's much more common is during the build process, dependencies are fetched on the fly. Maybe they're fetched from the internet. Maybe they're fetched from an internal trusted repository. Regardless, they are fetched and used in the build process. All right. So an artifact, that's kind of a blob. It's an output of a build process. While building, you can have attestations, these authenticated statements about metadata, and a specific type of that is provenance, what happened. Okay. And so just to bring things together a bit here, here's another diagram of during that build process, we are making from source code some artifacts. Here we've got multiple different types of artifacts. From one build system, from one set of code, we're creating a package. Let's just say it's a container image, but we also are creating provenance, right? So while I was building it, we had a scribe off to the side, just talking about, holding all of the metadata, writing all the information about what happened, storing that in a provenance attestation, and then storing that right next to the package. So in this case, we said it's going to be a container image. The way that actually works is if you're building a container image with provenance, typically you end up with what's called an image index. An image index is a special type of manifest for container images, which is really just a list of lists, right? It is a pointer to the actual container manifest and a pointer to the provenance manifest. This is exactly how multi-platform images work. If you have a newer MacBook Pro like I do, and it's on an ARM-based chip, you need a special type of prerequisites, ARM-based compiled artifacts. But if you're on an x86 system, those are different. So you don't have to say which of those you prefer when you're doing a Docker run or a Docker pull. That platform is used, it's detected what system you're on, and it requests the specific manifest for a container image that matches your platform. There's really a list of them behind that Nginx that you're trying to run, or BusyBox, or what have you. That same technique is used to store provenance in the exact same bundle as the actual container image. Right? Now, as you build systems, make that image, make the provenance, then you want someone to use it, right? Like the goal is somebody wants to use this thing. Maybe it's internal, maybe it's external. You've probably got that consumer should have a set of expectations, what they expect to be there. And so the goal is not just for us on the supply chain side to make the artifacts, but it's very important that the consumer verify them. If we just make the artifacts, very little security is gained. But if the consumer verifies those artifacts on the fly prior to leveraging them, that's when we get security. So there's two parts to this ecosystem. We need to, when we're producing artifacts, we need to do that responsibly and securely. And our consumers need to validate that. And vice versa. If we are using dependencies, we need to validate that our dependencies have this these artifacts, these attestations. So let's move on. Let's take a little bit deeper into provenance. So again, provenance is a special type of attestation, and it's for an artifact. It has a subject, and that subject points to an artifact. So if you look at the bottom here, I've got kind of a human readable version of provenance. This is not what it actually looks like in the real world, but the goal here is to help us understand it better before we go to the next slide and see it in a little bit more detail. So we've got a subject. The subject of this provenance is an artifact. It's a container image. That container has a hash, right? SHA-256-11BE5, right? In reality, it'd be much longer, but we've got this subject. It's an artifact with a given hash. Then we move on to the predicate. Where did this subject come from? It was built from GitHub Actions, from this specific hash, this git hash of this repository, github.com/foo/foo. 7ffd2 is the git commit hash of the code, right? So here we've got a repository. We've got that high integrity of a git commit hash of the state of the code. And then we're linking that to the actual artifact that came from your CI/CD pipeline, from a CI/CD pipeline, right? And then we've got a cryptographic signature at the end to say this, the provenance itself cannot be tampered with. Okay. So that was the human readable. This is the more detailed version of the same thing. So in reality, this attestation is all bundled up in what's called an envelope, a DSSE envelope, a dead simple signing envelope. And here in this example, we're using in toto. See that right here, in-toto. That's a CNCF project, rather common and popular, that helps to describe these different attestations, like software provenance. So we are making an envelope of type in toto, and we've got a payload. In that payload, we've got, what are we talking about? Again, if you think about the prior slide, we had an artifact with a SHA hash. Here we've got just a slightly more verbose version of that same thing. And we've got that predicate. So here we're going to be looking at a software bill of materials predicate in the format of SPDX. That's one of numerous formats that you could choose for this subject, right? For this set of code, right? So we are connecting code with the output of building that code and the thing that someone would actually use. So the goal is we're trying to link things together back further and further and further. And one question you might have is, well, don't we need to trust the first thing? Yeah. Ostensibly, our goal is to be able to have a strong root of trust, some really important initial activity that we do trust, which is handled much differently, and then everything from there is a chain off of that root of trust. Every step in a build process, every CI/CD pipeline, every commit hash to your repository, all of that with integrity, cryptographic signatures, provenance, all these sorts of things. So provenance, we talked about provenance. That's what happened in the pipeline. How do I connect together the Git repository and the Git commit hash to an artifact? So the next thing you might think is, I want to do that. I want to make sure my supply chain security is good. But it seems like there's a lot to this. How do I start? What's the first thing do I do? Then the second thing, then the third thing. What's the roadmap? And so that's where SLSA comes in. So SLSA is the supply chain levels for software artifacts. Its version 1 was released in April of last year, and there are 3 levels, right? Build level 0, 1, 2, and 3. Build level 0 has no requirements. So by default, congratulations. All of your code is at least SLSA level 0, build SLSA level 0. Then there is a defined pathway to improve your software supply chain. Starting with provenance, what we just talked about is essentially the first step of SLSA. So build level 1, we've got provenance. And again, if you see the focus over here, it's very interesting. We're not actually trying to reduce tampering or attacks or things like that. It's more about mistakes. It's more about documentation, right? It's more about just baseline quality. And after that level 1 is then when we start to get into taking things to the next level. Take that provenance and have it cryptographically signed. Make things generated from these host platforms. We want to reduce tampering after the build. So we do things during the build to make it hard to tamper with after the build, but during the build, it's still maybe susceptible. Then we can get to level 3. That's a hardened build platform. We want to reduce tampering during the build. And if you remember, there's all kinds of different things, dependencies, build, source, etc., that were issues. And we're not talking about all of those. We are just talking about during the build stage, how do we go from having nothing to improving our quality, reducing the likelihood of tampering after the build, and then reducing the likelihood of tampering during the build. And so this is just a start. This is version 1. There were other versions. Version 0.1 had a level 4, which talked about two-party review and hermetic builds and things like that. That didn't make it into the final release, but V1 is not the end. I also talked about the build track and having 3 levels for the build track, but there are other tracks that are now in progress. So you can see here, I linked to a couple of those issues where source, dependency, operations of your build platform are being worked on to define levels for different tracks, right? So lots of different things are being worked on here. Again, it's a very new ecosystem. And this whole salsa build track that we have right now, again, very focused on provenance and that artifact authenticity. And we need to make sure that we're not just creating the provenance, but that we're leveraging provenance where it's available. And when we're consuming software, we're checking it, and our consumers are checking it as well. Maybe that's other business units, maybe it's other companies. So by now, you're probably feeling like this is a bit of a fire hose. Luckily, we've got this recorded, but there's a lot of different parts to this. And again, they're fixing and focusing on different parts of that pipeline. Next, we're going to talk about software bill of materials and SBOMs, extremely popular to talk about. There are a few different standard formats, but 2 of them really stand out. Cyclone DX and SPDX. So SPDX came from the Linux Foundation. It's been around for a while. Its roots is more in licensing than anything else, and it's kind of grown in other directions, whereas Cyclone DX is a newer specification. It's now in the OWASP ecosystem, and it has a slightly different focus where it's been earlier to market on some security vulnerabilities and more other sorts of more comprehensive list of components and things like that. But we're actually going to take a look at that in a minute here as well. But use caution. So software bill of materials, a lot of people see these as key parts of your software supply chain, and yes, they're really important. But it's not the end. And even having them doesn't mean that you've solved the problems that SBOMs can solve because of the maturity of the ecosystem. So use caution, right? If you have container images and you're using a tool like Trivy or Sift or something like that, and you're trying to make a software bill of materials, the way that that works for container images, if you remember container images, these are zip files. It's just a bunch of different zip files. Each layer of an image is a zip file. And you just unroll those into the same directory, they overwrite some files, and then eventually you get the file system of a process that the container runs as. Those are just files on disk. And so while finding out that you've got version 1, 2, 3 of package A in there might be easy if it was installed with a package manager, it could be extremely hard if it was installed by someone curling something down. How would the tool that makes the SBOM know that this thing that was curled off the internet is package A and in a way that we can trust? Sure, it could have a file name, but how much do we actually trust the file name? Just look at the contents. Depends on what the contents are. Is this a compiled artifact or is it like a Java jar file, which is again another zip? Sometimes these things have metadata. Sometimes that metadata is incomplete. So identifying even what the package is, and then especially the version, reliably finding the version of the package can be very hard, especially when you have redistributors of software that will add patches and they maybe just don't change the version, or they make custom changes to the version that are hard to categorize. It's not actually from package A. They don't have a version 1.2.3 dash, alpha or, whatever. That doesn't exist, but the redistributor maybe patched, they cherry picked some commits, put it in there, rebuilt the package and distributed it, and that's what you're using. Well, now your software that makes the software bill of materials needs to be able to make that connection and know, and it could be really tricky to do. And so what I like to say is that those tools fail ignorant. That means that they just, when they can't tell what something is, often they just disregard it. They don't include it in the SBOM. So that leads to missing components. This thing is really in your container or really in your package, but it's not in your SBOM. Or it could be fewer CVEs. If it can find the package but can't figure out the version, how could it know which CVEs matters or which ones don't? They had to make a choice. They could choose to blow up your SBOM or your vulnerability scans with lots of findings, lots of CVEs, or none or fewer. Typically, the answer is fewer if you're doing, again, vulnerability scans of SBOMs and things like that, or tools that combine both SBOMs and vulnerability scanning. So these tools fail ignorant. They fail essentially kind of like closed, right? We just don't know that the thing's in there. So how much can we trust the SBOMs? You know, only as far as you can throw them, right? And another big thing with SBOMs is that on their own, excluding some things we'll talk about later, they really only talk about the contents of an artifact, not whether or not it has a vulnerability. That is a thing that you can kind of link in. Certain specifications have support for it. We'll talk about that in a little bit, but typically we're just talking about what is in there, and then you have a secondary step to vulnerability scan those and find what CVEs or issues, backdoors, malicious code are an issue. And this is becoming more and more predominant. I was just on a call the other day, and we were talking about a medical device company that's working on a new medical device. And as of October 1st, the FDA requires SBOMs for medical devices. They're not the only one. In the executive order we referred to earlier, there was a big focus on having and evaluating SBOMs for government entities. And kind of that is beginning to pervade the software ecosystem in general. In the CNCF, we've had a huge focus on improving the supply chain security of the CNCF projects, and that includes adding SBOMs, provenance, doing cryptographic signing of our artifacts, using ephemeral environments, all of these different ecosystem things. But it's a lot of work. It's not easy. A lot of parts to this. All right. I promised a demo. Let's do a quick demo. Let me just refresh my page here. So we talked about a lot of different things. We talked about salsa. We talked about SBOMs. One thing that we didn't talk about was cryptographic signing. I will show a demo of that very briefly. So this is our flight simulator that we use in the new version of SANS Sec 540. You can see I've got all this sort of code on the side. I've got a terminal here, and then this is where files will show up when we get to that point. So I'm going to just expand that up. And let's download some things. So I'm using the GitLab command line to interact with my GitLab CI/CD system and version control system. I'm saying in CI, let's download an artifact off the main branch, the SBOMs for our AWS DM API application. So we've got SBOMs here. We've got a few different versions of them. We've got that Cyclone DX that we talked about, the OWASP standard, SPDX, the now ISO standard, previously from the Linux Foundation that was donated. And then we've got one standard that's specific to a tool called SIFT. Now, what could we do with these? Well, first, let's just take a look. Let's open them up. Move this down a little bit, and just get you an idea of what this looks like. So this is a SIFT format. Let's go to one of the more standard schemas. So here we've got Cyclone DX. It is format Cyclone DX spec version 1.4. And you can see there's lots of different metadata. In fact, we used the SIFT tool version 0.9020 to create this Cyclone DX SBOM. If we go down, you'll see a whole litany of different components, and you'll see some really important keys and values, right? So of course we see versions and names and groups and things like that. We also see pearls, these package URLs, these ways to uniquely identify a package. This will be really useful in the future. A couple slides in the future, I'll talk to you about how you can leverage those pearls to do some really interesting things. We can also do linkages. So we don't have to have redundant information. We can point to other things using high integrity cryptographic hashes, right? So here we've got cryptographic hash. We've got all of these different properties. of the artifacts in what we scan. And I'm just going to scroll. You can just see the scroll bar over here is barely getting touched. There's so much in these, so much metadata, right? And again, this is a fail ignorant like system. So if it didn't have a way to parse, if it's regular expressions, literally regular expressions, were not good enough to be able to identify with high level of confidence that it was a package of version whatever, it may not be in here at all. So briefly over here in SPDX land, same exact artifact that was scanned, same tool, same version, right? SIFT 092.0, but you could see a different format, a little bit more condensed, but the same type of information, right? And you can see this one also very similarly is quite long, quite lengthy. All right. So that's great, but what can I really do with this? Well, just as a single example, and let me just maximize that, and I'll make it a little bit bigger as well. You can see here that because these are JSON outputs, we can use a tool like JQ, and we can look at all of the packages in this SPDX. SBOM, like I said, SPDX origins are focused on licensing because it was for open source, making sure that we didn't inappropriately use certain types of licenses. So you can see this command just takes all of the packages in the SBOM and groups them down to what license they have. And then we can see all those licenses here. Now you can see we've got some that are probably fine, MIT, Apache, MPL, and MIT, etc. Some that are a little bit more custom, right, throughout here. That might require a manual lookup what the Antler license is, Eclipse license, things like that. But then we've got this big 391 no assertion, right? So that means that the package, that the SIFT tool was unable to identify what the declared license was for a given package. So we've got lots of we don't knows, right? Hundreds of we don't knows. In fact, majority of we don't knows. This is the ecosystem, right? There's something in there, but it just says no assertion. That should not make us warm and fuzzy that we can use this, right? How do we improve the quality of this data? Well, this is an evolving space today, right? And there's all kinds of other things that you can do with this, but we're going to just move on for time. Let me just clean that up. Let's take a look at salsa provenance. So salsa, right? Supply chain security levels for software assurance, software artifacts. So there's levels 1, 2, and 3 in version 1. And the way that the salsa attestations are stored is in a provenance document, right? And so again, going back to how this gets stored for a container image, this is a separate manifest behind an image index. So there's multiple images, multiple manifests in this image. One of them is the actual thing that will run, and one of them is provenance, and it's all bundled up into one big pile. So we're going to run this big long command, and we can see the actual provenance of this image. So I'm not going to go through all of this, but if we jump to the end and we'll go up from there, we can see, skip through a little bit of this. You can start to see lots of data about the source, about files that were used to construct this image. There was a Docker file. We've got different hashes of files and locations. We've got information about layers of base images and all kinds of useful information, right? If you needed to dig into it, the information is there. We could go back in history. So that's great. And again, you can see it's this big, long command here, but that's not super useful to me today. Maybe what I want to do is I've got a Docker image, and I want to see what the Docker file was that was used to make the image. So you can do that too. So you can see here, I'm using Docker's buildx. That's the build kit builder. and we're inspecting the image name, which I pulled up above. And then we've got this big old blob here, which is selecting specific information from the provenance, right? And you can see if we go here, we're looking at the salsa metadata, then the source info, then we're checking to see if the file is a Docker file, and if so, we're going to print the data. And that data is base64 encoded, so we're going to decode it. And then that gives us this. We've got the original Docker file. So this, I do not need access to the source code directly in order to see the source that was used to create this file. It's in the provenance that's stored as a part of the image. I can actually go back. I can connect backwards in the pipeline. Usually we only think of forwards. We had a Docker file, then we created an image. Now this allows us to go from an image back to a Docker file with this provenance, which is also cryptographically signed, right? So I said cryptographically signed. We didn't cover that a ton, but let's just really briefly take a look at how you could cryptographically sign that image. In fact, we did already cryptographically sign that image with there's a project called SigStore, which is an umbrella. They have multiple tools underneath them. One of those tools is cosign. Cosign cryptographically signs images. And you can see here we've got a public key. We're going to need that to validate the signature, right? There's a private key that signed this thing, and we're going to use the public key to validate it. So we are going to grab some information from HashiCorp Vault. We're going to extract a manifest of the image that we want to look at. And then we're going to run this cosign verify. So you see cosign verify, we're going to point to the public key, and then we're going to use that image name and digest and kind of parse it out. This right here is the output that cosign gives you, the context about what was signed. And you can also see it's a little bit obtuse, but in this block right here, we're saying the signature is validated, right? The signatures are good. So this verified. We had a cryptographically signed image, and we just checked it by having access to the public key, and we're good. There are other things that you can do here too. I checked a manifest digest, but I don't know about you. When I want to use an image, I don't like manually key out the manifest hash. I just don't do that, right? This massive thing right here, I don't know to look at that. I use tags, right? So tags can be included in the cryptographic signature. You can see here, I'm going to extract this optional field called tag, which we did include, and we can see that this manifest has a digest which maps backwards to the tag. So if you've seen like a common trend here, historically we've been thinking about going forward. So supply chain is about linking things backwards and forwards. All right. So you can add arbitrary metadata in there. You can have approvers. You can say that John Ziola approved this image to go into production. I can put that into the cryptographic signature, set it up, store it in our ECR environment. And when our Kubernetes cluster goes to deploy it, it can check, hey, only if one of these 5 people approved it, will I let that in with a validating admission controller. If you watched the last of this series, we talked about admission control a lot. Ben Allen did a great job covering that. You could have an admission controller validate only if these people approved it, it can go to production, or only if it went through a pipeline. We have a private key. It's only available in a pipeline. So by being signed by this private key, I know that you went through the pipeline. I check that public key. I validate it using the public key. I can be reasonably assured. It's not perfect, but I can be reasonably assured it went through the pipeline and it's allowed. Right? So there's all kinds of different things that you can do in the supply chain world. And we're improving that assurance with lots and lots of different solutions, to be honest. All right, so that's our demo. We've got just a handful of slides left, and I'll open it up for questions. So if you've been thinking anything, feel free to throw that into the Q&A, and we'll cover that in a few minutes. We said before, software bill of materials can be useful to tell you what ingredients are in your artifacts. But what if you want to talk about the vulnerabilities? And what if you specifically want to say, this vulnerability does or doesn't matter, right? Have you ever done vulnerability triage and saw a false positive, right? I definitely have been there. There is a new specification called the Vulnerability Exploitability Exchange, or VEX. And there's different ways you can express this. So on the left, I've got one standard called OpenVex. On the right, I have Cyclone DX's standard, just so you can see two of the few options that are out there. And what this does is it allows you to connect together. Excuse me one second. It allows you to connect together dependencies and components from your SBOM to vulnerabilities to a status of that vulnerability. So on the left, we have an example of status affected. This is a problem, right? That's what we're saying. We're saying CVE 1, 2, 3, 4, 5, 6, 7, 8. We know about this vulnerability and we are affected. Okay. Now you can programmatically, if you give software to other departments, they can choose what to do with that. All you're saying is I'm affected. They can choose to not use or to use your software, to do different sorts of incident response or logging or mitigations. We're now sharing knowledge in a better, more programmatic way. Now, alternatively, we don't always have to say things are affected. We can say that it's not affected, and we can have justifications for that. So on the right, we did an analysis of the CVE 2020-25649, and we're saying this is not affected. For our system, this is not affected. Why? Because the code is not reachable. So yes, we are using the version that has the dependency. I'm sorry, the version that has the vulnerability, but we don't use the part of the code which is vulnerable. We don't use that code path. It's impossible. So for us, you cannot exploit that. So yes, when you run a vulnerability scanner, you're going to find that issue. But I am programmatically telling you to disregard that. Now, you can choose whether or not to trust me. This does not mean you need to trust me. All I'm saying is, as the software vendor, the author, that I've looked into this, and this is my assessment. You can choose to trust or not to trust me. And it's also possible that we can have whole ecosystems in the future pop up around this, where companies assess software and say, oh, this does have this dependency, but I agree, it's not reachable. The code's not reachable. Now you could have multiple attestations, multiple VEX statements saying that this is not reachable, not affected, and only in the aggregate do you trust it. Only if there's 3 people, only if Google or Alpha Omega Project says that it's not reachable, do I trust it. You could set your own rules, your own automated policy, right? So this unlocks an entire new world of transmitting information across producers and consumers of software, and especially across company boundaries, organizational boundaries, which I am a huge, huge fan of. So remember I said at the beginning, after we talk about baseline supply chain security techniques, we're going to talk about day 2. So here I'm demonstrating where different solutions fit in this whole supply chain hierarchy. There is a project. We talked about salsa, right? We showed SigStore and cryptographic signatures in the demo. So that's like our kind of a trust foundation. We've got these software attestations. And on top of there, we need to aggregate lots and lots of data. That's what Guac does. So you can tell Guac, salsa, we've got a lot of chips and dip going around, I guess. So Guac is a graph that also supports the index and retrieval of information based on SBOMs. It can go find more information whenever you have a pointer in an SBOM. It can gather that context. And then you can have clients, you can request from your Guac graph, tell me everywhere in my company we have this problem. Here's all my SBOMs. And then a query, how many times, in what situations does this matter to me? It's a scale problem. When we make all of these artifacts, we have to do something with them. We have to organize them and analyze them and visualize them. That's what Guac does. So there is these newer ecosystems. If you look at, I think it's guac.sh, and if you Google guacsec on GitHub, you can find the open source Guac project. And then on top of all of that is policy. right? We're talking about governance, and governance is actually something that I'm extremely passionate about, but is not the topic of this presentation. If you ever want to talk about automated policy as code, and governance, that's really a huge part of what I love to talk about and do. That is the kind of very overarching part of this ecosystem. We need to say what's allowed. We need to say that we need to check these things. We only trust things from Alpha Omega, attestations from Alpha Omega, but not these other companies. You set that policy broadly, and then you implement that with policy as code tools. And maybe those turn into queries of the Guac graph, or using salsa provenance, cosine signatures, etc. These other things are like the building blocks that allow you to roll up to corporate decisions, compliance decisions, security choices, trade-offs, risk management, right? Another quick mention is OSCAL, the Open Security Controls Assessment Language. So this is a NIST project, and it is optimized for expressing this information right here, right? So this is a schema. You can have it in JSON or YAML or XML. And it's a way to, again, transmit information across boundaries, across organizations. So if you have compliance needs and you need to get FedRAMP certified, OSCAL is extremely popular for that use case, specifically because it comes from NIST, but also useful in other use cases like a SOC 2 or ISO or any sort of other requirements, even regulatory requirements. You could express what you're doing to meet those, what controls you have in place, how you've checked that those controls are working, and that includes things in the software supply chain. These things that happen in the software supply chain are security controls, right? And so you can express in OSCAL these security controls, how they're in place, and then give that information to auditors, to your customers, to regulatory bodies, to show that you are doing the right thing, and also to prove to yourself that you're doing the right thing. I love tools like this so that we can check ourselves and make sure that we're doing everything that we need to be doing. And finally, if you're interested in policy as code or governance, risk, and compliance, but you've been interested in how that would work in a super modern environment, we came out with a white paper. This is another group I'm involved with, the Security SIG, and specifically the policy working group in Kubernetes. We came out with the Kubernetes GRC white paper. This talks about how governance works in modern ecosystems, how OSCAL fits into this, as well as there are other accompanying white papers. There's a policy as code white paper and more. So lots of great resources out there. If you go to the SIG Security GitHub repo, you'll be able to pull this down as well. So quick conclusions. We've only scratched the surface of this whole ecosystem. This is its own subfield of security. It's got lots of point solutions today, lots of problems, its own vocabulary, really its own whole ecosystem. There's a lot to it, but it's a really important problem. We've got the executive order. We've got 750% year-over-year increase from the 2021 Sonatype report. This problem is not going anywhere anytime soon. The impact is getting bigger. We have more code reuse. So this is just the start of talking about this problem. I would also like to just point you all to some good additional open source materials. In the CNCF tag security, we came out with the software supply chain best practices. That's a white paper on how to follow some of these best practices. We have the secure software factory, which is a reference architecture, more specific. And there's even a project called Fresca, FRSCA, which implemented in code the secure software factory, so you can see it working and operating in the real world. And then you can take pieces from that and see how you might want to do it in your company. Of course, a lot of these materials and information comes from the Sec 540 Cloud Security and DevSecOps curriculum. So if you're interested in that, feel free to pick up one of those classes. Come hang out with me in New Orleans in a few weeks, or we'll talk a little bit later about other classes that are coming up. So let me take a question or two before we wrap up. So I see I've got one here. Very interested in OSCAL. I see the GitHub you listed, but is there anything else from a resource perspective you recommend to get started with OSCAL? So yes, I would This awesome OSCAL is not from NIST. This is a kind of public resource, and it's a pointer to lots of other resources. The NIST documentation right here, pages.nist.gov/OSCAL, is where I got this screenshot from, but there's lots of other good materials there. There's what's called the Metaschema project as well in that ecosystem, something else to take a look at. And there are lots of events, especially if you're in the DC area, you can expect, because this is a NIST government-funded project, there's lots of things happening around the DC area talking about OSCAL. In fact, I think there's an event in a few weeks that I'm going to be going to in DC that talks about cloud compliance and has lots of roots in OSCAL, lots of conversation there. If you're interested, feel free to shoot me an email or connect with me on LinkedIn. We could talk more about OSCAL as well, but I would recommend starting with the NIST documentation, the awesome OSCAL list, and then that will point you to lots of presentations and code and things from there. All right. Any other big questions? Yeah, don't forget at the bottom of a lot of these slides, I've got links to the references, so feel free to check those out. Like I said, connect with me on LinkedIn or send me an email. My information is over here if you want to talk about this stuff more. If this was an interesting topic for you and you want to learn more, you want to go deeper and broader, we've got a whole slew of different SANS classes, all the way from our baseline classes, the 300 series, 388, up to the core. We've got 540. This is the class that I teach right here, and lots of others. We have blue team, attack, and defense, lots of different specializations for microservices and application security, and pen testing, and even leadership classes, right? Cloud security for leaders. And you can see, I love these flight plans. So if you're focused on becoming an engineer, an architect, a manager, we've picked out kind of the classes that fit better for that career progression. So feel free to check those out. Also, like I said at the beginning, this is a 4-part series. Today is part 3. So we've already covered GitLab, we've covered Kubernetes and mission controllers. Today was supply chain. Next, we've got Eric Johnson. He's going to be talking on February 15th about least privileged pods in Kubernetes and Kubernetes workload identity. So definitely check that out. That'll be very interesting. If you feel like you missed either part 1 or part 2, you can get access to the recording. And if you're interested in any of the upcoming classes, we've got some online and in person. So I'm going to be teaching in Orlando in March, as well as I have a New Orleans class towards the end of February, just in a few weeks here. There's also an India live online class that Ahmed's going to be teaching. We've got Santa Clara, California, Oslo, Norway, in person and live online. So feel free to check all those out. Go to sans.org/sec540 to get all of the upcoming classes that go even further out than this. All right. Well, that's everything I've got today. Thanks everybody for coming out. Hope you enjoyed it. Again, feel free to reach out if you've got any questions, and good luck securing all your supply chains. Have a good one.